Hello. Let's start with the talk. Today, I will cover some of my research on Apache HTTP web server, and I will show you also some of the vulnerabilities that I have found during this process. But first of all, who am I? Well, I am Antonio Morales. I work as a security researcher at GitHub. That is my Twitter handle, where I usually post most of my research. And inside GitHub, I'm part of a small team called GitHub Security Lab. Our main goal in GitHub Security Lab is to improve the security of the open source software. This is just an example of our work, and I encourage you to visit our website. This is the link to know more about our team and the research that we do. And in my case, I mainly focus on C and C++ projects. I'm also a Fuzzing enthusiast, and more specifically, an AFL and AFL++ fan. And these are some examples of software in which I have been working on during the last year. But today, I'm going to focus only in the Apache HTTP server security. Okay, so the agenda for today has these 5 points. In the first one, I will show you a brief introduction about the Apache architecture. In the second one, I will show you a summary of my fuzzing workflow. Then I will go over some of the custom mutators that I have built and why I have built these custom mutators. After that, I'm going to explain some of the custom interceptors that I have created. And in the last point, I will show you some of the vulnerabilities and bugs that I have discovered. Well, let's start with the Apache architecture overview. Apache is one of the most well-known HTTP web servers. So I think that it doesn't need any introduction. So we can skip this slide. Okay, and Apache's architecture is composed of 3 main parts. The first part is the Apache core that includes some basic functionalities of Apache. Then we can find the modules. The modules implement most of the functionalities of the web server. And then we have the APR, the APR library, the Apache Portable Runtime Library. And between these modules, we have 5 different categories. The first one is the npm modules. These type of modules are responsible for basic request handling and dispatching. Then we have the base modules. These are modules that are compiled and loaded by default. We also have the extension modules that are not normally loaded into the web server, except for a few cases. And out of the Apache distribution, we can find also the experimental modules. Those are available into the Apache distribution, but are not officially supported by the Apache team, by the Apache developers. And the last group is the external modules, that are those modules that are not included in the Apache kit. And a very important type of modules are the npm modules, the multiprocessing modules. These provide an interface between the Apache server and the operating system syscalls. Between the tasks that the npm handle, we can find, for example, creating the network connections, listening for requests, and accepting requests for the clients. And npm also can handle the creation of processes and threads. And it's important to note that we can only have one npm running or loaded at the time. Well, between these three main modules, we can, or best said, we can differentiate three main modules on Unix systems. The first one will be the pre-fork configuration that implements just a pre-fork web server without threads of any type. That is how the old versions of Apache used to work in the past. The second npm configuration is the worker npm. This npm implements a hybrid multi-thread and multi-process server. In this npm, each process creates a fixed number of threads. And the last one, that is the newest one, is the event npm. In that case, it's an asynchronous implementation. And the main difference with the worker npm is that the event npm is able to reuse a single thread for new connection. So it doesn't need to open a new thread or for every new connection. And then we have the third main component of the Apache architecture, the Apache Portable Runtime. APR is a supported library for Apache. It provides a set of APIs that make possible to use the same functions across different platforms, across different operating systems. And some of the capabilities of APR includes are the memory pools and memory allocations that I will explain after. Also handle the file input and file output. Provides also shared memory functionalities. And for example, other things as multi-threading or time routines. And this is the Apache operation diagram. It has three different phases. The first one is the Apache startup. This first stage includes the parsing of the configuration file, the loading of libraries, and the initialization of the system resources. The second one is the operation phase. In this stage, the first thing that Apache does is to call to the setUID function in order to change to a regular user, from root to a regular user. It also includes the request processing itself. And the third one is the cleanup phase. In this last stage, Apache releases all the resources, including memory, file handles, or sockets. Now I will show you an HTTP request and how this HTTP request is processed by Apache. For example, we have our HTTP request here. And at first, this HTTP request will go through these metadata modules. Then the output of the metadata modules will be processed by the input filters. After this, the request is processed by the handler modules and by the output filters. The last stage is the execution of the logging modules. And amongst the metadata modules, for example, we can find modules for URL preparsing or modules for HTTP access and authentication. As a filter examples, we can find, for example, modules for encryption or for compression. Well, Now I'm going to explain some of the most relevant aspects of my fuzzing workflow. I have divided my fuzzing workflow in 4 different parts. Choosing a fuzzing engine, socket fuzzing, important code changes, and fuzzing modules. Well, choosing a fuzzing engine. When it comes to the fuzzing engine, I don't have any doubt. AFL is my choice by default. AFL++ is a fork of AFL, but it includes a lot of new features in comparison with the original AFL. Amongst these features, I can mention, for example, custom mutators, or power schedules, or multiple instrumentation modes. Another problem that we face when we want to fuzz an interactive server is that AFL doesn't support native sockets fuzzing. So we need to find, or we need to modify the source code in order to be able to fuzz the server. For that, my approach was to add a small code snippet into the npm code that I showed to you before. This snippet code self-connect to the server itself, open a new thread, and redirect all the input data through it. Let's look at these 2 code snippets. You can see the self-connect function just here that establishes a connection to the server itself. You can see here the local host. And what I do then is just to read the file data, it's here, and send this data through the socket. These code snippets will be then introduced at the npm source code. And in my case, I use 2 different fuzzing configurations. Most of the time, I use the prefork npm, mostly 80% of my time, with only 1 process at a time, with the aim of getting a good stability. But I also fuzzed the event npm in order to catch concurrency bugs, so to catch concurrency issues. Let's see now some changes that I made to the source code in order to improve the fuzzing process. For example, the first group of changes are aimed at reducing the entropy. For example, in that case, replacing calls to random by constant values. Here, you can see that I comment out the generate random bytes call, and instead, I use a constant seed. The main idea is to reduce the entropy of the execution. The second group of changes are aimed to reduce delays. For example, removing some sleep or select calls. The idea here is to improve the fuzzing speed. And you can see here, as I comment out, the select call. The third group of changes are those made in crypto routines. For example, to disable checksums. In this picture, you can see as I comment out both CRC comparisons, here and here. And that's really important because otherwise the fuzzer will get stuck in this CRC. So this is always a critical moment when we are preparing the fuzzing. Okay, and now I will show you my approach for fuzzing the different Apache modules. What I did was to use at first an incremental approach where I started with a small set of modules enabled. You can see here the HTTPD conf. And then I try to progressively include new modules in the configuration file. And test the stability. Following that, I repeat the process until all the modules are enabled and the fuzzing process is stable. Okay, let's give now a brief introduction about custom mutators. So, what's the problem that we want to solve? Well, by default, AFL and LibFuzzer implements basic mutators, like, for example, bit flipping, byte flipping, known integers. So these mutators provide good results when applied to binary formats, but are not so good when applied to complex formats, like, for example, the HTTP protocol. So my solution was to include additional custom mutators specifically created for fuzzing the HTTP protocol. You can find all the code related with these custom mutators in my GitHub repository. This is the link, Antonio Morales. And for example, in this first example, we can see a simple custom mutator, the line swapping. You can see here two different HTTP requests, the GET request and the POST request. And below, you can see an example of mutation where the content type and the accept language, you can see as these headers have been swapped. So now the POST request has two different accept languages headers, while the GET request don't have any accept language header. In this second example, we can see a word swapping. That just swaps two words, or more specifically, two parts of the URL. In the picture below, you can see as the HTTP request, get hello and post, have swapped their URL. Now the post goes to hello and the get goes to CGI. Well, but I have implemented also some other custom mutators, obviously. For example, I implemented a charset brute force mutator. These mutators were inspired by Hashcat password cracker tool. And for example, I implemented things like 2 bytes brute force, 3 bytes brute force, strings brute force, digits brute force. And in addition to use custom mutators, I used custom grammars. For this task, I used the grammar mutator tool that is included into the AFL++. And to use grammar mutator, we only need to define a JSON file that includes a collection of key and value pairs. This is a part of my grammar specification. Here you can see it best with an example. For example, you can see as every request is composed of a start line, then we have an end of line, then the headers, the body, and the end of the request. And at the same time, every single start line is composed of a method, for example, get, head, post, the URI, and the HTTP version. So this is a part of a custom grammar. Well, and now it's time for custom interceptors. But first of all, why do we need to implement custom interceptors? Well, things are going to be a little bit harder there, but don't worry. So, as I previously mentioned, Apache uses custom memory pools to improve dynamic memory management. For this task, Apache uses the functions that APR, the Apache Portable Runtime, provides. For example, if we want to allocate memory inside the memory pool, we need to use the APR palloc instead of the standard malloc, because we want to allocate memory inside the memory pool. So consider the following code snippet, where the program calls to APR palloc. In this case, the second argument that, okay, so we want to allocate, for example, 126 bytes inside the first argument, inside the APR pool. This is the size argument, and this is the APR pool where we want to allocate the memory. So this is how Apache memory pool works. The Apache memory pool consists of a linked list of memory nodes. Each node has a fixed side memory available. You can see here the memory of each node. And as you can see also in this picture, the third node has some free space available. Then, when more space is needed, the program will add a new node just at the end of the list. So if we don't have memory, obviously we need to add a new node to the linked list. And this is the code of the allocator alloc function. And the thing is that this function, as you can see in this comment, round up the minimum size to 8,192 bytes. And of course, this will be a problem for address sanitizer. So for example, I can show you a scenario where we make a call to APR palloc with a size of 126 bytes. Here you can see the output of the debug. So, and this is the output of the debug in the allocator alloc function. So we have made a call to APR palloc with a size argument of 126 bytes, but address sanitizer has poisoned a memory area of 8,192 bytes. So the result is a total area of 8,066 bytes, marked as writable by address sanitizer. But the thing is that this is not real allocated memory. Instead, it's free space in the node of the list. So for example, imagine that we call to main copy with a size of 5,000. This will lead to an overwrite of the rest of the node's memory, because our buffer is of 128 bytes. But, however, address sanitizer will not throw any alert message because, address sanitizer poisoned a memory area of 8,192. So, will not throw any alert. And the thing is that errors like this can result in vulnerabilities such as the one I published 1 year ago in Pro FTPD. This is the CVE of the use after free that I published 1 year ago. And this use after free has a public exploit released. Okay, so how we can solve this? So to solve this, we can define our custom address sanitizer interceptors. To define our own address sanitizer interceptors, we need two things. The first thing is to define an interceptor function like this, where the foo is the name of the function that we want to intercept. And the second thing is to call to the ASAN intercept function before the first call of the function foo, or prior to the first call of function foo. And this is just an example. This is my implementation of my interceptor for APR palloc. There are three relevant parts. The first one is when I call to real APR palloc to get the original address of APR palloc. Then I save the address of the sanitized malloc. And in the end, what I do is to save both addresses to free them later. Obviously, if we define custom interceptors for palloc or whatever malloc derived function, we will need to define also custom interceptors for the free functions. So in that case, what I do in the first step is to free all the addresses previously allocated with the address sanitizer version of malloc, and then we can proceed to free the memory allocated with the libc version of malloc, with the standard version of malloc, the libc. Cool. So now it's time for the most expected part. Now I will show you some of the vulnerabilities and bugs that I have found. I'm going to start with a null dereference in the session identity decode function. As you can see here, this bug can be triggered setting a cookie with a null key and value. So look at this example. That clarifies the thing. In the first position of the cookie, we have the session key and the choco value. This is the first position. In the second position, we have the admin user key and the number 2 as a value. But in the third position, we have an empty key and empty value pair. What's the problem here? Well, if you look just below, you can see two calls to APR string token. These functions try to extract the first and the second value that are the key and the value of the cookie. So that said, let's see what happens in the string token function when the first argument is null. Just look here that we have the pair string, but the second can be null if the key was previously null too. So you can see in this line how the while loop try to dereference the first argument, the string argument. So in order to in that case, it will lead to a null dereference, obviously. And in order to exploit this bug, mod session needs to be enabled. And this vulnerability can lead to denial of service at the child level. That is, affecting to the other threads in the same process, or affecting to the other clients that are connected to the server. Okay, now it's time for another vulnerability. In that case, it's a stack base off by 1 in the check nonce function. In order to exploit this bug, the mod auth digest module should be enabled. And the application has to be using the digest authentication. Here you can see the digest. And for triggering this bug, we need to assign a specific set of values or a specific value to the nonce field. You can see here the nonce field. As you can see, the nonce field is a base 64 value in the nonce. So then the check nonce function does a call to the base 64 decode binary in order to decode this 64 value, base 64 value. The thing is that the first argument is a local array of size 8. This is the first argument. But here below you can see as the calculation of n bytes decode variable is grown, giving 9 as a result. So in this case, 9 bytes will be written into an 8 bytes buffer, writing 1 byte out of the boundaries of the array in the stack. Okay, let's see the third vulnerability. Here we have an use after free in the cleanup tables function. This function calls to RMM destroy, as you can see in this line. The thing is that this memory has been previously freed by the APR allocator destroy function. So when we are trying to access to an address that is no longer valid, it will lead to an use after free, or in this case, sometimes to a use after free and some other times to a double free. It's important to mention that this vulnerability can only be triggered in the one process mode. Okay, another one. In this case, we have an out of bounds write in the heap. The off by one, the previously explained off by one was in the stack, and this is in the heap, affecting to the escape quotes function. This function escapes any quotes in the given string. The origin of this bug is a calculation mismatch between the length of the input string and the size of the allocated outstream buffer. Here you can see the allocation for the outstream buffer. So in this first code snippet, I show the code that is used to calculate the length of the input string. And in this second picture, you can see that the code for calculating the size of the output string is different. As a result, if we provide a malicious input to the escape quotes function, it's possible to write out of the outchar array. That is, it's a pointer to outstring, the outstring array. Unfortunately, this bug was previously reported by Google OS as fast, just a few days before I found it. So it was a bug collision. And now I'm going to explain something totally different. In this case, this bug is a race condition leading to use after free and affecting to the Apache core. So during my fuzzing research, I found multiple bugs that I wasn't able to reproduce again. After going deeper in that, I discovered a kind of race condition between the allocation function, like for example that, alloc, and the destroy functions of APR. This leads to a corruption of some nodes of the memory pool. And sometimes the program will try to release a node that is already present, or a block that is already present in the free pool. At this moment, it's important to note that it only happens when the NPM is the even NPM. That is the standard de facto nowadays. And at this moment, I'm still trying to figure out how to exploit this vulnerability in a deterministic way. That is the problem with this type of race condition bugs. Of course, there are some stack traces examples. I have a lot of them. In this case, we have an use after free. As you can see here, it's an use after free. Look at this stack trace. We have the APR allocator destroy, the starting with the npm in the event npm. But look at this one, for example, to here, a totally different stack trace, but related to the same problem. The stack trace is totally different, as you can see, and it's the same problem. You can see here even the same read size of 8. And the thing is that thing or this problem is not a new problem. This is a problem that has been reported a few times. Not exactly the same problem, but this type of problems has been reported in the last years. For example, I would like to mention to Hanno Bock that reported this bug at first time, or this type of bugs, 3 years ago. If you are interested, you can check it in the following link, their original reports. And for now, the position of Apache security team is to not consider these security issues as a problem unless we can show a practical exploit. So I'm working on it. And something similar happened the last year with Pro FTPD. We found a new after free in the memory pool of Pro FTPD that at the same time is based on the memory pools of Apache. And at this moment, there is a public exploit that has been released to exploit this vulnerability. But anyway, and during my fuzzing session, obviously, I found a lot of other minor bugs. So I would like to show you one of them. That is an integer overflow in the session identity decode function. In that case, it's not a dangerous bug, but I think that it's interesting to show one example of how trivial or how easy is to trigger this bug. For example, you only need to send a log webdap request. Here is the request with a long timeout value. But don't get messed. I mean, this is not an overflow. I mean, we provide a really long timeout value, but it is an integer overflow. I'm sure that most of you are able to identify what is the problem. Marco, I'm sure that you are able. Okay, perfect. That's perfect. Here we have the addition of 2 integer values, you can see here, that will be stored in another integer value. So if these values are big enough, we can overflow the returned value, because obviously we cannot store in an integer the addition of 2 maximum integers. That is a typical integer overflow. Since this bug is triggered with a log request, mobdap should be enabled in order to be able to trigger the bug. Okay, and now I would like to say one last thought. Apache HTTP security has been extensively studied by researchers, but at the same time, there is still room for discovering new vulnerabilities. For example, using fuzzing. And in the coming weeks, I will release new details about Apache HTTP security, including new bugs. So stay tuned. So that's the end. Thank you to all of you for attending. And now it's time for questions. Thank you.
Thank you, Antonio. Is there any question? Yeah.
I know I already asked yesterday, but I think this might be something interesting for everyone. How much time did you invest in this specific research?
In that case, or in general? In this specific case? Well, I'm not going to, I don't know. I'm not able to estimate exactly, because I mean, I put a lot of effort. But It depends. It depends. It can take. I'm not going to give you a number. I don't want to. Maybe later I can give you an answer privately, you know. But it takes a lot of time. Yeah. No. Yeah, no. I mean, at the first slide, or well, you can see that in the last year I have been working on too many different projects. So you need to be able to find vulnerabilities in a lot of projects in the same year if you want to work as a security researcher. Yeah. Yes. Any other question?
Any other question? Yeah.
Come on.
And while doing this specific research, on the exploitability side, are there any bugs which are actually like easy to exploit in a real world scenario, or most of them like needs also like, I don't know, a memory leak or whatever to be exploited?
Okay, there are like, what I usually look, or what I usually try to find with fuzzing are memory corruption bugs. So there are like two big type of bugs. There are logic bugs and memory corruption bugs. So logic bugs, for example, if you are able to find a logic bug, probably you only need one bug to be able to exploit the server. But nowadays, if you find a memory corruption bug, it's very common to need at least 2 or 3 different bugs because probably you will need a memory leak, probably you need another great primitive, like, for example, I don't know, a stack buffer overflow or use after free, heap overflow, and then you will probably need another vulnerability to escalate privilege. So yes, probably it depends on the type of vulnerability. In this case, 1, 2, or 3 vulnerabilities. Yeah.
Okay. Thank you very much.